So have you ever wondered how a self-driving car actually sees the road? Or how we get those incredibly detailed 3D maps of, say, an entire forest? Well, the answer, more often than not, is this really cool technology called LiDAR. Today, we're going to pull back the curtain and see how machines use laser light to understand the world around them. You ready? Let's get into it.
Okay, take a look at this. This isn't from a movie or a video game. This is a real-time 3D map. It's called a point cloud, and it's being created right now by a car's LiDAR sensor. Every single one of those dots you see is a precise measurement in space. It's what gives the car this, superhuman awareness. The big question is, how do you get from invisible beams of light to a crazy detailed map like this? Well, that's exactly what we're here to figure out.
All right, here's how we're going to break it all down. First, we'll cover the basic idea of seeing with light. Then, we're going to peek inside the sensor itself. After that, we'll talk about the main types of LiDAR out there, weigh the pros and cons, and finally, look at where this tech is already changing our world.
First things first, let's follow the journey of a single pulse of laser light. Probably the easiest way to wrap your head around this is to imagine shouting into a big canyon and listening for the echo. LiDAR does basically the same thing, but it's using light instead of sound. And oh yeah, it's doing it millions of times every second. So what even is LiDAR? The name itself is actually a huge clue. It stands for light detection and ranging. And that's really what it is at its core. It's a way of sensing the world by actively shooting out pulses of laser light to measure distances with just incredible accuracy. And that's the fundamental process that lets it build those amazing 3D models we saw.
The process itself is, brilliantly simple when you boil it down. Step 1, the sensor fires off a laser pulse. Step 2, that pulse travels through the air, hits something, a tree, another car, whatever, and it bounces back. Step 3, a detector back in the sensor catches that little reflection. And finally, step 4, the system's brain calculates exactly how long that whole round trip took. And this right here shows us how the math works. It's all about something called time of flight. The distance to an object is simply the speed of light, which is a constant, we know that number, multiplied by the time it took for that round trip. Then you just divide that by 2. So why divide by 2? Simple. Because the pulse had to travel there and then travel all the way back. This time of flight idea is the absolute bedrock of how LiDAR works.
Okay, so we've got the principle down. Now let's actually look under the hood and see the hardware that makes it all happen. What are the key parts that make up one of these laser eyes?
What you're looking at here is a cutaway of a classic mechanical LiDAR sensor. You've got a laser that fires a beam upwards, and it hits a mirror that's spinning incredibly fast. As that mirror spins, it sweeps the laser beam across the environment, painting the world with light. When the beam hits something and bounces back, a receiver catches it. It's that constant spinning motion that gives the sensor its famous 360-degree view.
So, if you boil it all down, any typical LiDAR system has 5 main parts. You've got to have a light source, which is your laser. You need a scanner and some optics, like that spinning mirror. You need a photodetector to catch the light coming back. For any unit that moves, you need a positioning system, like a GPS. And last but not least, you need a processing unit, the brain, to make sense of all that raw data and turn it into a useful map.
It's also worth knowing that not all LiDAR lasers are the same. Most of the sensors you see on things like cars and robots use what are called micropulse systems. They're pretty low energy and totally eye-safe. But then on the other end of the spectrum, you have these super powerful, high-energy systems that scientists use for stuff like studying the atmosphere.
So that spinning sensor you might have seen on top of an early self-driving car, that's just one type of LiDAR. As the technology has gotten better and cheaper, the designs have really started to evolve.
In this slide gives us a perfect side-by-side. On the left, that's the mechanical LiDAR we've been talking about, spinning around to get that full 360-degree picture. But on the right, that's solid-state LiDAR. See the difference? It has no major moving parts. That makes it way more compact, much more durable, and a lot cheaper to make. All things you really want if you're going to build it into the body of a car. The main trade-off is usually a more limited, forward-facing field of view.
And then there's a third way of doing things, called flash LiDAR. Instead of scanning one little point at a time, it works just like a camera's flash. It illuminates an entire scene with one big pulse of light. A special detector then captures that whole scene at once, instantly creating a 3D depth map. It's incredibly fast, though it usually works best at shorter distances.
So, LiDAR is this incredible technology, but, like any tool, it's not perfect. It has some really distinct strengths and some pretty clear limitations. Let's take a look at the trade-offs that engineers have to think about when they decide to give a machine the power to see with lasers.
But before we list the pros and cons, it helps to know how we measure a sensor's performance. Engineers will look at stuff like its range, how far it can see, its resolution, how much detail it can pick out, and its accuracy, how precise those measurements actually are. Things like these determine which kind of LiDAR is the right tool for the job. All right, on the pro side, the biggest advantage by far is accuracy. LiDAR is just exceptionally precise. And because it brings its own light source to the party, it works just as well in total darkness as it does in the middle of the day. It's fast, it's super reliable for spotting obstacles, and it's the tech that creates those amazing data-rich 3D maps.
But there are definitely challenges. For one, LiDAR is still more expensive than a simple camera. Its performance can take a hit in bad weather. Think heavy fog or rain that can scatter the laser light. It also creates these enormous data files that take a ton of computer power to process. And finally, while it's amazing at telling you something is there, it's not so great on its own at telling you what that something is. Is it a person? A plastic bag? That's why it's so often paired with cameras.
Okay, for our last section, let's zoom out from all the tech specs and look at where this technology is actually moving out of the lab and into our daily lives, because its uses are spreading way beyond just self-driving cars. Of course, autonomous vehicles are the most famous example. But LiDAR is also crucial for robotics, letting warehouse bots and drones map out new spaces on the fly. It's used on airplanes to create these stunningly high-definition maps of the Earth. It's used in farming to check on the health of crops, and even to scan whole cities to help plan for smarter infrastructure. When you really think about it, LiDAR is fundamentally changing how machines perceive and interact with the physical world. It's giving them a rich, accurate 3D understanding that just wasn't possible before. And that brings us to a really fascinating final question. As this technology gets cheaper, smaller, and more powerful, where are we going to point these new eyes next? What will we choose to see?